Okay, so I'm Radostin Cholakov from Bulgaria, and together with Todor Kolev from Obecto, we worked on the problem of task-oriented dialogue systems and how to make them more efficient by employing auxiliary warning. So let me begin with some of the canonical approaches to task-oriented dialogue systems, which rely on modularized systems to generate a response to a given question or a request from a user. And the task-oriented agents usually have to fulfill a certain task, for example, hotel reservation or public transport booking and so on. And the traditional systems rely on language understanding module to extract the entities and the SWOT from the text, decide what the intent is. Then a policy making module is deciding what the agent should do next. Should it request more information or confirm that the task is fulfilled? And finally, based on this knowledge, a language generation module creates the final response, which is then given to the user. But now, with the development of deep learning, more and more systems are relying on end-to-end architectures because they can internally learn some of these abstract decision-making tasks. And in our work, we are first taking a state-of-the-art baseline architecture for task-oriented dialogue modeling, developed by Johan Lee, which is based on the T5 language model and is codenamed TOD. And as you can see here, this end-to-end text-to-text language model is able to internally learn the different steps of the decision-making and language response generation, and to rely on this deep learning architecture for the whole decision-making process. So the T5 model here has an encoder which generates the latent representation of a given input and some conversation history with previous utterances. And based on the latent representation, we actually have not one but two decoders, the first of which is a belief decoder, which generates autoregressively a belief state containing what the agent is thinking the user is asking him. And then in the middle, we may have a database query or some hook to a third-party service. For example, if we are building a system for hotel reservations, we may have the access to their database. But in our work, we don't focus on this part. And then based on the generated belief state, one more decoder autoregressively generates a system action and a response. And in the way it works, after the system action is generated in the output utterance, it automatically, the encoder is conditioned to on this system action to then generate the natural language response. And this simulates the previously described steps of canonical task-oriented dialogue systems, but in an end-to-end fashion. And previous work has demonstrated that auxiliary warning is able to make these end-to-end systems more efficient. So the auxiliary warning is the method of designing conditional tasks together with one or more primary tasks. And then during training, the loss of the additional task is generated, the loss of the primary tasks are computed, and the parameters of the primary task are updated both with the loss of the primary task itself and also by the loss of the additional tasks, with the intuition that it might positively affect the primary network. In our work, we propose two variants for a response selection auxiliary task, which takes a part of the previously presented end-to-end system and given some internal representation of some of the outputs of a part of the system. We are feeding these latent representations to binary classifiers, and then these binary classifiers, in our case, perform two response selection tasks. In the first case, the binary classifier should distinguish destructor responses from ground truth responses, meaning that when the user asks a question, we pick from the dataset the ground truth response, which the system is expected to give, and we also sample one wrong answer, which is answer to another question. And then we're using the T5 encoder, which is the same encoder used in the primary network, to generate latent representations of the conversation history concatenated with the true response and the conversation history concatenated with the destructor response. And these two latent representations are then given to a classifier, which should decide which is which and assign one class to the true responses and another class to the sampled wrong responses. And during backpropagation, this positively affects the T5 encoder, which is then used in the primary network during inference. And in a second, I will show empirically what the results are. And the second variant of our response selection tasks actually try to distinguish between synthetic responses generated by the end-to-end model and the ground truth responses. So it works in a way that first the system itself, the decoder generates a response to the question, and then we get from the dataset the actual true response and give the two responses to a classifier, and it should decide which response is generated from the network and which is generated by a human. As you can see probably here, there's a small problem with the second variant because it is working with sentences that are generated from the primary network in an autoregressive fashion. And when that happens, we are usually, for each and every token, we are selecting from a probability distribution the highest probable token or some of the highest probable tokens. But this operation is not differentiable in the way presented here. And that is why if we just use the most probable token out of the distribution of probabilities from the response decoder, when the generated sequence is fed to the auxiliary head, then backpropagation won't actually affect any part of the primary network. And to solve this challenge, we actually sample from a Gumbel softmax distribution. So we add some Gumbel noise to the probability distribution of the tokens generated by the response decoder, and this distribution here is parameterized by the this hyperparameter tau, which is representing the Gumbel softmax temperature, and high Gumbel softmax temperatures mean more biased and less variant samples from the probability distribution, and as the temperature decreases, we are getting more and more higher and higher variance samples. So during training, usually when we are doing this approach, we should employ a scheduler to begin with a certain amount of temperature and then decrease it over time. and the exact procedure is described in our paper and on our repositories. So to give you an idea of what the experiments were, we worked with the multi-Wizard of Oz dataset, which is a large-scale corpus containing human-to-human conversations in multiple domains. And here you can see how a cleaned and pre-processed version of the conversation looks like. We're having some question posed by the user or some request, and then the system returns a response where some of the tokens are masked with SWOT tokens in order for us to be able to replace them if we are having an actual database or an actual third-party service that is working with this chatbot. And we trained in an auxiliary warning fashion these two variants. You can see here on the screen the warning curves for the first variant, where we are selecting from the structure responses, and the second variant on the bottom, which is distinguishing between synthetic and ground truth responses. And the main results and the simple result I want to point out here is that the baseline model developed by Johan Lee without any selection tasks and relying on the T5 base backbone, which is having more than 300 million parameters, is performing on multiple metrics comparably or even worse than our two variants, which are relying on selection tasks. But they are actually using a smaller version of the backbone, the T5 small backbone, having just a little bit more than 100 million parameters. And the metrics here are the informed success and bilingual evaluation metric, which are combined in a fashion that the first two are added together, divided by 2, and then the blue is also added to generate the combined scores. This is done in compatibility with previous studies in the field, which have also experimented with the multi-Wizard of Oz dataset. And as a future work, we are thinking of testing this proposal on even bigger models to test it, for example, on the T5 large backbone, but not only that, but also explore different architectures for transformer end-to-end text generation. And we are also, of course, thinking of adding more auxiliary tasks, different variants of the response selection task or another types of tasks, which can also positively impact the primary network. But the interesting question here is actually, can we combine multiple of those tasks? If two tasks are combined together, will they actually improve the primary network even more, or they will cancel each other out, and so forth? And also introducing data augmentations is another way of trying to increase the fluency of the responses in such a system by providing different sentences with the same semantic meaning, but augmented in different way and making the system produce the same or similar responses. And as a conclusion, I presented the work in which we built a response selection as an auxiliary task approach to enhance task-oriented dialogue systems. We're testing it with a backbone that has previously been declared one of the state-of-the-art solutions to multiple task-oriented dialogue datasets. And we are able to show that employing such auxiliary tasks, we can derive comparable performance or even slightly better performance on different benchmark metrics even though in some cases we are using smaller models in terms of trainable parameters, making the system more production ready and more usable by researchers and actually also companies. Thank you for your attention, and I'll be happy to answer any questions.